Paul is the sort of the expert or premier first generation modeling person. I've known her for almost 10 to 15 years. And she works from NASIC, basically coming out of Pune University, Dr. Dilip Kanhare's group. But over the years, she has developed her own reputation in doing calculations, basically magnetic materials, including clusters. So without further ado, let's welcome Dr. Deshpande for her presentation.
Hello.
Good morning, everybody. Today I am going to present the overview related to the different codes available for modeling of the materials. So basically, when we are considering the computer simulation, then you may use the word that is computer modeling, and generally that used to develop or explore the numerical models that reproduce the properties of the material, structures and process or the phenomena. So when we are considering the computational based project or the theory based project, then typically we have to ask some question before starting the project. So the questions are, what do you want to know? How accurate does the prediction need to be? How much time can you devote to the particular problem? And what approximations being made? So now when you give the answer related with this particular question, then you can define your particular model to run your project. So when we are considering typically the theoretical model, then these theoretical models are related with the, you can say, the material specific, and they will generate the universal properties. So our goal related with the theoretical computations are to identify the microscopic mechanism, then the experimental probes, and the predict new material or the structures. And for these purpose, the ingredients are your electrons, basically the valence electron you are considering, and you can handle these electrons by using quantum mechanics. Or in that case, you have to consider the many-body problem and how to convert that how to approximate that particular problem to get the particular answer or to get the particular data. So when you are focusing on these particular ingredients, then generally you can see this is the length scale related with your problem. So you are going from electronics to the autos. So you are saying that you are going from atoms to autos. So naturally, our vision is for the multi-scale material design, or you have to find out the material properties which will play a central role in designing the new devices. So when you are considering the atomic level or the atomistic computer simulation, which involves the modeling, then in that case we are handling the individual atoms or the molecules that make up the material. So in that case, generally we are using the ab initio. You are always listening this particular word, that is the ab initio or the first principle code, or you can say the quantum mechanical methods. So these particular methods are either depend on the potential approach, or they are depending on some empirical techniques which gives you some approximate, or you can say the data which is closer to the experimental one. So in that case, you have to select the method for the particular problem which depends on the size of the system, the type of the bonding of the material. So in that case, you can say that there are different types of the bonding, ionic, covalent, bivalent, so on. So in that case, you have to select the particular model to handle the particular data. So when you are considering the computational model, then there are three types of models: ab initio, semi-empirical, and the molecular mechanics. So here I have listed down these particular models according to their accuracy. So generally, the ab initio uses the Schrodinger equation, but with some approximations. The semi-empirical parameters are generally use some experimental data, and they are not using, or you can say that they are more simpler as compared to the ab initio, and the molecular mechanics are not using the Schrodinger equation. So when you are pictorially representing these particular techniques, then you can see that there is slight overlaps from the ab initio, semi-empirical, or when you are considering the atomistic tools to calculate the properties of the material. Now when you are focusing on the ab initio technique, because our focus is on ab initio technique. So in this case, when you are focusing on ab initio technique, then the ab initio technique translated from the, means you can say that this is the particular Latin words, that is a from first principle. And this refers to the fact that no experimental data is used and the computations are based on quantum mechanics. This is the main important point, that we are not using any experimental data in this case. So there are different levels of the ab initio calculation, the Hartree form, that is the simplest one you can say. But in this case, the major disadvantage of Hartree form calculation is that electron correlation is not taken into consideration. Then you have to consider the MP theory, density functional theory, or the configuration interaction. So all these theories are considering the electron correlation. So this is the, you can say, the small background related with the density functional theory. So when we are considering the Hamiltonian and you are writing all the terms related with the Hamiltonian, then in that case, if I want to solve this particular Hamiltonian quantum mechanically, then naturally I need the computer with the high memory capacity, as well as I need the large amount of time. So naturally I am saying that I had to access infinite computer to solve this particular Hamiltonian quantum mechanics. So we are doing some approximation, and in that case we are taking some electronic part and we are considering a part related with the nucleus. So in that case, when we are focusing on the different terms, then in a square you can see the terms related with the electronic part. Then the last term is the classical term. I am representing that term by EC, and which depend on the capital R, that is the nucleus coordinate, you can say. And the middle term I am cancelling, that is very small, because you are saying that the Mi is very greater than Me. So where here I am assuming that M is the mass of the nucleus and small m is the mass of the electron. So naturally, when you are focusing on the ground state, then approximately you can say that, or you can write down the particular equation that H, which depends on, or which is particularly is controlled by He, you can say electronic part, and you can write the equation for the ground state. So in that case, you can get a total energy, which is the, you can say the total energy function is the, means you have to say Z and R are the parameter related with the E total, and you can write down the term which is equal to Eg plus Ec. But in that case, when you are considering these two particular terms, then calculation of the Eg is the combination of these two terms. But in that case, the Ec is that Eg part, when you are considering, that is the ground state energy of the particular system, is more difficult to calculate. So for that purpose, naturally we have to do some approximations, and in that case, again I am going back to write down the many-body electron problem, and then you can see that how you are calculating the energy in that case. So you are saying that you are applying the variational principle, and you are saying that the E0 is the minimum of the expectation value of these particular things. So when you are considering this many-body problem and you are applying density functional theory to calculate the particular answer, then these are the basic terms which you have to focus, that the Wentworth theorem. Then you have to consider the different flows related with this, or you have to calculate the many-body system, and you have to consider the density related with the particular energy. So in that case, when you are focusing on this particular density functional theory, then instead of focusing on the typically, in this case for this ab initio method, you are saying that this density function theory is slightly different, because the wave function is not used to describe the molecule or the particular system, but you are considering the electron density in that case. So here your energy is dictated by the electron density. So this is the basic theory, you can say. You have to just go through this. So these are the, just I am skipping this. Okay, so again you have to read carefully about the Concham-Taylor. So these are the different approximations related with the density functional theory. Because when you are considering the term related with the electronic part, then the exchange part, you have to approximate it, and you can find out, you can do different approximations. So the first one is generally the local density approximation, or the NDA you are calling. So this is the basic expression related with the NDA. So in that case, when you are using the NDA, then there are some problems related with the NDA. So I have noted down the different problems related with the NDA approximation. So to avoid this, or to get the more better answer, you can use the GGA approximation. So in that case, when you are using the GGA, then there are many forms of the GGA available. You can use the PPE, you can use PW91. But in that case, when you are considering the GGA, then generally, when you are comparing the NDA with GGA, then you can get some different, you can say that there are advantages related to the GGA. So GGA lead to improvement in estimation of the cohesive or the dissociation energy, and the DFT. Generally, when you are considering this GGA with PD or PW91, then the chemistry people are preferring to use the GGA. So now these are the limitations related with the density functional theory. When you are considering the density functional theory, then NDA and GGA do not capture the media interaction and the forces. For the strongly correlated system, such as you can say modern insulator or the high TC semiconductor, in that case, you will the width of the bands related with base state are overestimated. When you are considering the lattice constant MBA, they are estimated by generally 2%. Cohesive energy, when you are considering, then it is overestimated in NDA by 20 to 40%, but better with GGA you can say. And the magnetic couplings are overestimated. And when you are considering the electronic dielectric constant, they are also overestimated. So generally, when you are using the DFT, then in that case you have to take one portion, or you have to carefully calculate. When you are calculating the band gap, you have to carefully focus on the band structure related with the particular system. So generally, when you are focusing on this theoretical background, small, you can say just overview related with the density functional theory, then generally the density functional theory in principle gives the good description of the ground state properties and the practical application of DFT based on the approximations for so-called the exchange correlation potential. The exchange correlation potential describes the effects of the Collins principle and the Coulomb potential beyond a pure electrostatic interaction of the electrons. Now, when you are considering basically the part related with the exchange correlation potential, then if you get the proper exchange correlation potential or the functional, then we get, or we can solve the many-body problem exactly. Means you are going towards the accuracy, or you can enhance the accuracy. So generally, if you want to start the calculation, or if you want to build the model, then generally we are starting with the local density approximation or the NDA. Okay, so when you are focusing on the general implementation of the DFT, then you can see the various methodology related with this. So in this case, I am just showing you the various parameters you can focus when you are implementing the DFT in your calculation. So generally, when you are focusing on the exchange correlation potential, then you can see this particular part. I have here mentioned the different exchange correlation. So in that case, the NDA is the initial one. You can say if you want to start some project, or if you want to learn some modeling, then you may start with the NDA. Then to improve your result, you may use GGA, but again you have to be careful when you want to use the NDA and GGA. Now beyond that, you can use different exchange correlation functional. So now the latest code may give you the hybrid functional related with this. So in this case, you can see the different parameters. Means when you are modeling your data, then you may use the periodic or the non-periodic system, or you can say some symmetrical system. The ultimate goal is you have to solve this particular equation. So naturally, you can do fully relativistic calculation, semi-relativistic calculation, or non-relativistic calculation. So these are the main charts you have to focus on, and according to that, you have to say that okay, which particular method I have to select, or in that case, when you are considering the different approximations, then you have to also consider if you want to use the atomic orbital or the plane wave, or which type of plane waves you have to use, or you have to use the augmented type of wave, you can say. So this is the particular chart you have to focus when you are using the DFT for the modulation work. So generally you have to say that there are three basic methods for the modern electronic structure calculation: plane wave, simple one. Then in that case generally we are using the fast Fourier transform. So with the plane wave generally we are using the pseudopotentials. When you are considering the second type, that is the localized orbitals, then in that case here we have to consider, or in this particular case there are different codes which gives you the localized type of orbital basis set. Then the augmented method, it consists with the characteristic of both plane waves as well as the localized orbital. So when you are preparing the model to run your system, then generally you have to divide your system either, means you have to find out whether your system is a finite system or the extended system. Then generally in the finite system, atoms or the molecules of the cluster when you are considering, it is called as a finite system. And when you are considering the extended system, then the crystal or the surfaces when you are considering, then in that case those systems are called as the extended systems. So here you can see one simple model related with this. So when you are considering the plane wave codes and you are using the particular model for the non-periodic system, then generally we are using the superset approach. So in this case, when you are considering this particular, then the interaction between the repeated images must be handled by sufficiently large vacuum region. So you have to take care when you are using such type of models or you are using such type of system. So generally in case of surface calculation, the thickness of the slab must be as large as possible. So when you are defining the model for your particular material, then you have to focus on these particular points. So when you are doing the calculations, there are three basic types of the calculations. So to get the particular information, you have to understand whether you want to use a single point energy, means just to find out the particular stability, or you want to find out the reaction mechanism, or you want to do the geometry optimization, means to predict the shape, or you can say that with this again you want to find out the lowest energy state as well as the low lying states related to the particular geometry, or you want to find out the spectra or the frequency spectra related to the particular system. So this is the general flow chart related with the computational procedure. So in that case, you are initializing or you are starting with the random wave function. You are calculating the density rho of r. So in density function theory, you are always when you are considering your energy at this particular function, you have to say that it is related with the density rho of r. So you are constructing the Bonsham Hamiltonian H, then you are applying some logarithm in between, and then you are calculating or you are checking whether the wave functions are self-consistent or not. So if it is self-consistent, then you are calculating the forces on the particular related to your system. Then you are computing the total energy and you are moving or you are in the next step. So in that case, you are checking whether the forces are in your particular desired criteria or not. If it is in the desired criteria, the particular computational procedure gets stopped. Otherwise, you will go back and you will repeat this procedure till you will get or your system satisfy the particular criteria. So generally, when you are considering this particular flowchart to run your model, then I will give you some examples related with some small clusters or how you can model this particular system. So this is the first example you can take where you are considering the small clusters of nickel boron. So by using the density function theory, you can find out the lowest energy state, as well as you can find out the low lying structures related with the clusters. So using, again, by further processing your data, you may plot or you may calculate the electronic properties of the particular system, and you may find out what type of orbitals are there, or you can plot the eigenvalue spectrum related with the cluster. So here you can also calculate the magnetization density. So you can see the spin up and spin down magnetization density related with the nickel and aluminum clusters. So you can calculate these type of parameters by density function. This is another example that you can calculate the spectrum for the small cluster. So you can use some codes which gives you or which generate the optical spectra related with the particular system. So here I am showing you the example related with the small cluster. So these type of calculations help you to find out the particular geometry method, or you may find out the low lying states related with the spectrum. So here you may apply this particular model for the nanowire interaction. This is one example that through which you can calculate the interaction between your system and the biological molecule. So this is another example you can relate with the visualization software, that how you can model your system. So in this case you can see that we are considering a particular molecule with a cluster and a biomolecule interaction. So you can define such system using some visualization software. So now the next question is, after looking at this particular example, how to select the code or how to choose the code. So naturally, one thing you have to remember, that the best code when you are selecting is the code that you understand. That is the main thing. That when you are starting something, then first you have to understand it carefully, and then you have to select the other code once you understand one basic code. After that, when you are considering the code which you understand, in that case you have to also focus on the approximation which you are doing related with that particular code. And in that case, the approximation means my focus is on the pseudo-potential, basis states and the K point. So when you are focusing on these particular parameters, then actually you will be able to run your particular system through the particular code. So in that case, you have to also focus on the approaches used by the particular code. And naturally, one more important point, that the CPU time and the memory used by the particular code. So you have to also see that how much CPU time is with you and the memory related with the particular computer system. So the computer requirement or the computer system is the major point when you are selecting the particular system. Now when you are running the calculation by selecting the particular code, then these are the steps. So when you want to run or when you want to take some product from your particular code, then naturally you are focusing on the pseudo-potential, basis point and the K points. So in that case, if you, by mistake, if you are not selecting the proper basis state or proper pseudo-potential, then again you have to rerun your calculation. So in that case, this particular flowchart gives you the setup for your particular model or the material which you want to run using some particular model. So in that case, when you are comparing the particular output from a particular model with the other, then you may generate some meaningful data through your calculations. So now, that is something. So actually, when you are selecting the particular model or you are selecting selecting some code, then here I am going to give you some, you can say, interest related with the codes available for the either for the classical calculation or for the biomechanical calculation. So in that case, generally, when you are considering the different codes, then DULP is one of the code which is generally a multi-purpose program for the simulating the crystal. Nowadays, people are using GLOMAX, and this is the MD program for the biomolecular sciences and the biotechnology. So there are different codes. So these are the different codes you can use to run your calculations. Generally they are DL Poly, or you can say VMD or DL Moto. This is basically used as the Monte Carlo simulation. then the music is one of the codes, shell is another code. VMD is generally used to generate the symmetry of your particular material when you are optimizing that, and it can be used as a visualization package when you are generating the particular data. Now when you are focusing on the quantum mechanical operation, then the Abinit or the Impro or the Big DFT or the Castate are the different codes. So now in this case you can see these are the different codes. So games or the GPAV or Phonon, Phonopi, quantum espresso. So today we are going to learn about the quantum espresso. So there are the hands-on sessions related with this. So these are the general code which are calculating the electronic structure related with the particular system. So there is CSR, then to calculate the excited state properties, or you can say the optical properties, the 3DFT is the code, or there are many more codes which you can use to calculate the properties of the material. So here you can see, in short, the peculiarity related with some popular codes. So I am taking just some example related with CSR or the quantum espresso or the Gaussian or the Bahas code. So in this case, when you are considering the CSR, then this particular code gives you it is an efficient program, you can say, to calculate the electronic structure calculation and the ab initio molecular dynamic simulation of the molecules and the solids. So here this is the one more interesting point related to the CSR. So in this case, the CSR efficiency, when you are considering, then it strictly uses the localized basis sets and from the implementation of the linear scaling algorithm which can be applied to the suitable system. And very important feature of the CSR is that its accuracy and the cost can be tuned over a wide range. So from, you can say, in that case, if you want to see the output from the CSR, there are ready-made examples you can take from the website and you can run directly those examples on your system. And one peculiarity related with the CSR, that with CSR you are getting one more package, that is a trans CSR, and this trans CSR gives you to calculate the transport properties of the particular system. So you may calculate your IV characteristics, so in this case you can design your device and through that you can calculate the IV characteristic for a particular device. And you can check the transport properties related with your system. So this is related with the quantum espresso. So generally it is an open source package. So CSI is also open source package. You can download it and you can install on your computer. So in this case, you can calculate the ground state properties, self-consistent total energies, forces and the stresses through the quantum espresso. And generally it provides you the ultrasound or the Mandelbrot to the potentials, PAW, that is the projected augmented waves. So in this case, it also provides you the several exchange correlation forms from ND8 to GGA. In GGA you are getting these number of, you can say, the exchange correlation functional. So after quantum espresso also gives you the hybrid functionals. So you can calculate different properties using the quantum espresso. So here you can again consider another code that is related with the Abinit. So from this you can calculate the total energy, charge density and the electronic structure, means like density of states or the projected density of states using the density functional theory. So in that case, this particular code can be applied for the molecules as well as the periodic solids. Then it also gives you the pseudopotential and the plane wave approach. You can calculate these properties using the Abinit code. So VAST, it is a licensed software, which you have to purchase the license and you can install it, but it is one of the popular code to calculate the magnetic properties of the system generally. So in this case, when you are considering the VAST, these are the characteristics related with the VAST that it gives you. Means it generally uses the periodic DFT program in 3 dimensions, plane wave basis set. It also gives you the pseudopotential approach. So in that case, the convergence when you are considering related with the VAST, it is fast and the optimization methods are very efficient as compared to the other code. So here there is no basis set. So you can avoid the superposition error related with the basis set. So in this case, when you are considering the VAST code, then it is slightly difficult to calculate the accurate reference energy for the atoms. But generally you can calculate the other electronic properties like the charge transfer analysis, that is a better charge, you can calculate, and you can use different functionals to get the accurate answer, or you can increase the accuracy of your calculations. another code that is a DMOL. So it is a first principle code, quantum chemistry software, that performs the accurate theoretical calculation on a wide range of compounds, you can say, including the metal clusters, biological systems, or organometallic or the organic compounds. So that is the peculiarity related with the DMOL group. So again, you can calculate the number of parameters or the electronic properties related with the particular system. Then here you can see the another code that is a crystal. Nowadays we are using, or there is a crystal 14 which is a major release from this crystal code group, and this is you can say it the calculate the typical parameter, you can say, that is the first and second hyperpolarizability is calculated through this particular version. The band structure loss you can calculate, and you can calculate the Raman and IR intensities through this. So generally, when you are focusing on the crystal, you can calculate the structural properties, you can calculate the vibrational properties, you can calculate the electronic structure and the magnetic properties of the system. And also with that, you can calculate the dielectric properties of the particular material. So naturally, the another, you can say, the popular code that is a P2K. So in that case, this package also performs electronic structure calculations of solid, again by using density functional theory. And it is based on full potential, that is a linearized, you can say, the augmented plane wave, that is LAPW, plus the local orbitals when you are considering. So in that case, you can select the particular parameters and you can run your calculation. So this particular package is all electron scheme, including the relativistic effect. So you can use this particular package to calculate the particular property. Now if you want to calculate the optical properties, then there is another code is available for us, that is a parsec code, and this particular code solves the Pancham equation by expressing the electron wave function directly in a real space. So this is a main peculiar characteristic related with the parsec. So without the use of explicit basis set, this code is again uses in that case the non-consuming pseudopotential, and it is designed for the ab initio quantum mechanical calculations of the electronic structure of matter within density functional theory. So in that case, this code also helps you to calculate the structural parameters related with your selected system, or the optimized geometry you can find out. You can run the simulated annealing, means you can find out the exact ground state using this particular code. Then you can calculate the polarizability, you can calculate the optical properties using this particular code. So in that case, you have to use the one supporting system with the parsec, that is the RGWDS code, which helps you to calculate the optical properties using this parsec. So there is another code related with the calculation of the optical properties, that is the Octopus code. So again, Octopus is a scientific program, you can say, aimed at the ab initio virtual experimentation. So in that case, this particular code uses the TDDFT, that is time dependent density functional theory, similar to the parsec, and it gives you, or typically this particular code is used to calculate the optical properties of the particular system. Then there are some professional softwares. You can purchase this particular software. One of the particular software is the Material Studio. So in this case, the Material Studio is the complete modeling and the simulation environment design, which allows you to design your system as per your requirement, and you can find out the particular properties of the particular of the system. So in this case, generally this particular software is used to calculate the catalytic property of the particular system, or you can apply, you can design the composite system and you can calculate the properties of the composite system. So there is another professional software, that is a NanoLab. So this particular software again you can use with the different software. So this particular software takes the data from different cores like VAS, Quantum Espresso, or there are some other cores like GPAW, and that data you can supply to the NanoLab and you can calculate the properties. So now once you generate the particular data, your task is to visualize that particular data. So for the visualization purpose, you have to use the different packages. So this is the least related with the visualization packages. So generally these particular packages you can get easily, and you can install on your Linux based system, or some of the software are Windows based. So in that case, generally with the Fedora or with the Linux system, you can get Avogadro software. So you can see or you can edit your system position, or you can say the atom position, and you can design your own system by using Avogadro. So this is one of the software where you can analyze the crystal and the electronic structure of the particular system which you are taking as a model. Then the model is the software. I have shown you the example related with the model, that you can design or you can visualize the you can say the model which you are designing, you can visualize to the model. Then the Vesta is one of the software. Then VIMES, you can say the visual interface to material simulation, this is another software. But the popular one are the model, XCrisDen, KGraphView, XSmallView, and nowadays on Windows system generally the people are using WXDragon. So this is one of the software you can use to update, or you can modify your input, and you can take the another run to find out the next problem. So VMD is the another. So in this case, when you are considering all this course or the visualization package, then to start with, you sometimes require the hint to design your input. So there are some standard database from which you can take the input to start your calculation. So these are some of the standard database. So this particular Cambridge structural database gives you the number of cluster initial geometry, and from that you can build, by using the visualization software, you can build your own cluster and you can run the system. So this is the, you can say these are some databases which gives you the, you can say the slabs, or you can design your thin films, or you can design your cluster slab interaction, like that way. So you can use this particular database for the manipulation of your system or to start. Now there are some online utilities which always help you to start some atomistic simulation. So these are the online, you can say, the websites you can see, and from that there are some ready-made examples. You can take those examples and you can start with these examples, and you can understand the code which you are or which you want to select. So these are the online tutorials you can take. There are many more, but I'm just giving you the examples related with the tutorials. So through this you can also learn how to run or how to simulate or how to model your particular system, and how to take the run through the particular software. So these are the main books related with the density functional theory. So if you are interested to understand the density functional theory, you can go through this particular book, and then you will understand the theory behind that DFT calculation, and then you will enjoy the calculations which you are interested in. So actually when you are handling any code, then you have to be aware that when you are running any calculation, you have to understand first what you are doing. So in that case, you have to also understand the limitation of the present DFT functional, and then you have to select the proper code to run your calculation. So thank you very much.
Floor is open for questions, comments.
I want to know about this SCF procedure.
SCF procedure. Okay.
Please remember, this is an interactive session for students. So I'll make sure I'll come to students and ask the student to ask the question. So watch for my eyes.
So this is the procedure for the SCF calculation, you can say. So when you are considering the inner part related with this, so this one.
This is complete algorithm.
Right. But in between, I have shown this is a self-consistent. Or here you can take the self-consistency. So I have not shown exactly the self-consistency part. I am showing here you the complete computational procedure.
This is the DFT algorithm.
Right. Right.
But what self-consistent?
So here you can see here you can see the particular steps related with the self-consistency related with the particular
So what's
requirement.
going inside this SCM process?
Right.
That's the I want.
Yeah.
So can you tell him what is the input? What do you need to first put so the program takes over? What are the
Yeah.
inputs?
So when you are, if you want to run only SCF calculation, then generally we are focusing on the electronic part. So we have to give the positions of your particular system. Suppose you are selecting a cluster, then in that case you have to give the position of your, means atomic position you have to give to the particular program. Then it will start by considering the pseudopotential. Suppose you are considering the pseudopotential approach, then it will select the pseudopotential, and you are suppose using the plane wave. Means I am adding one by one point related with the SCF. So you are suppose considering a pseudopotential, means mass code you are using. So in that case you are selecting the pseudopotential, you are selecting a particular gamma point calculation because you are handling the cluster system. So in that case, to run the self-consistency, you are simply giving the position of the particular atomic position as an input to the particular code, right? And in that case, it will start doing the calculation on that atomic position by selecting the pseudopotential properly and at the gamma point you can say. And on the electronic part, it will take the self-consistent calculation.
Like in mathematics, the self-consistent iterative methods.
Yeah.
Same thing we do in our Gaussian program.
Right. So it is an iterative process. Until and unless when you are not considering the equilibrium position related with the electron, you are not considering the nuclear position in that case. So first you have to run the self-consistently on the electronic system, and then you are moving towards the nuclear part. So in that case we are considering that is the calculation of the forces.
So let me ask what is the criteria when you think that your calculations converged?
Yeah, so generally when you are considering the self-consistency, then in that case, for each core we are using certain criteria for the force as well as for the electronic equilibrium part when you are considering. So generally we are using 10 raised to minus 4 or 10 raised to minus 5 EV, that is the energy criteria for the self-consistency cycle. So in that case, when you are satisfying this particular criteria, then you will become out and then the forces get calculated and so on.
So I think let me follow one thing is suppose he wants to use Gaussian for MgO molecule.
Yeah.
So what do you need for MgO?
Yeah. So suppose you want to run the Gaussian code for the MgO molecule, then in that case you have to first prepare your input file. So in that case you have to select means what type of basis set you want to use. So either you can select D3LYP and so on. Then you are selecting or you are giving the position. MgO molecule you are selecting, so you have to give the dimer position in your input file of the Gaussian. Then you have to define the potential which you are, you are using the basis set. So you are defining B3LYP and you have to give the particular distance between the Mg and O atom when you are selecting. And then you have to simply on the flag related with the SCF calculation. When you are doing the optimization, then you have to do that particular flag in the Gaussian. But for the SCF cycle, you have to select that SCF flag, you have to make it true and then you have to run the calculation. So it will give you just for a desired distance the properties related to the MgO.
So this is a two-step process. One is we use Born-Oppenheimer approximation. We fix nuclei and we calculate the SCF cycle. What is the total energy, minimum total energy by variational principle for the given position. And like Dr. Deshpande said, then you vary the position and you recalculate. So our idea is energy is less than 10 power minus 6 R3, position force is about 0.01 electron volt per angstrom, this is But what I tell all the students is the idea is do not go to very, very high accuracy in the beginning. Because you have to, I call, feel the system. Just use a very poor basis set, very poor functional form, and just run it to see what kind of physics you get it. And once you have feel the system, then you start adding more and more accurate parameters. Question? You should ask question. Green. Yeah. First, can you give your name and introduction so we know who you are?
My name is Preeti Bhoryal and I am from IIT Indore. So my question is, is the VMD correction is important for single point energy calculation?
Which correction is that?
Right.
Sorry, VDW.
Now, when you are considering the VD fraction system, that is VDW, right?
Yeah.
Then in that case, for the single point, it means if your system is optimized and you want to find out the correct energy, then you may add that in a SCF cycle. But generally, in VAST code, we are doing this way, that we are adding that VDW correction in throughout the optimization, and then we are calculating the energy at the end of the whole calculation, means after optimizing the particular system.
Can't we use the tag in INCAR?
Yeah, we have to use the tag in INCAR file. Yeah, for the VDW correction. And also you have to refer that release paper, and according to that you have to add the parameter in your INCAR file. Those will always support to calculate the VDW interaction related with your system. So those will give you the correct energy.
Let me add to answer the question, what kind of system you are looking at?
For layer.
For layered, yes, then you have your VW. But always remember, for layered system, quick and dirty calculation is LDA. LDA gives you right sort of equal spacing, not the energy. So run LDA is fast, you get the peak of the system, then pick up LDA geometry. So rerun the calculation with the DGA with the van der Waals. So do sort of an incremental steps, because if you do directly with the VDW, it will take forever, and your advisor will not be happy. So run first LDA. LDA is quick and dirty. An idea is to get the LDA geometry for any system, and then use the geometrical parameter to do a sort of more advanced calculation.
Variation in energy levels. Actually,
She's the speaker, so ask her.
If we use LDA, what about the variation of energy
Yeah, I have
levels?
shown you the drawback related with the LDA and GGA. So when you are starting something at the first time, then always when you are focusing on the means whether your system is correct or not, whether you can run it. So in that case, LDA is always gives you the rough estimation of the energy. So don't focus on the energy at the initial stage. When you want a correct energy, then select the proper functional, proper basic state, proper pseudopotential, and then calculate the energy variation.
Thank you.
So energy is I call it a second order. First order is you have to get the correct equilibrium. That's the thing. You will have a few more questions. I think you're listening. Oh, okay.
My name is Seema Gautam. I am from IWCCMP Mohali. My question is, what is the preferable method for the slab calculation, whether it is a selective dynamics or the
For slab calculation.
Yes, for slab.
Yeah, generally we are preferring the slab, for the slab calculation we are using selective dynamics. Means you can freeze the lower layers, and if you want the surface interaction, right, then in that case for the surface interaction you can freeze the lower layers and you can just take the interaction with the upper layer. But if you are designing, means if you want to see the lower layer interaction also, then there is no necessity to freeze the other layers. You can do the full optimization.
Then we have to include vacuum also.
Yeah.
So without vacuum we cannot convert the cake.
No. You cannot get the convergence quickly.
Selective dynamics is very computational expensive.
Yeah, true. But in that case, again, you can use, if you want to see the interaction, then again you can go for a GGA type of calculation. You can run with the selective dynamics GGA, simple GGA, take the output, and then polish your output by using the higher functions.
Okay, I think you were saying that for the layered material LDA is better.
LDA or GGA you can use. But generally for the slab calculation, we are selecting the GGA first. We can calculate the, you can say the geometry optimization we can, yeah.
But in past we have only plane wave basis sets.
Yeah.
So,
But in that case, you can save your time by using the ultrasoft pseudopotential LDAs. And you can take the output. And once you get the field related with your slab calculation, then you can improve the pseudopotentials as well as you can select the exchange coordination function.
So let me add to this thing is VAST is plane wave based code. So what you can vary or play around with the less accurate answers, simply reduce the cutoff. use a 200 eV or 250, get the good configuration, and then you increase the cutoff. The cutoff is going to take a lot of time. And so supercell approach, you have to have a vacuum because you are basically mimicking the 2D slab. And if you don't use the vacuum, then you're going to have the slab interaction, slab-slab interaction. So we call, in order to minimize the periodic interaction of images, you have to have a vacuum of 50 angstrom. And I prefer to use for higher calculation 20 or 25 angstrom. But again, the computational cost is in this thing. So make sure first you consult your advisor. What does he want? If you want quick results, just do a LDA, very small cutoff, a very small vacuum distance.
But in that case, just one correction, that instead of using the VAST, you may shift to the siesta or Condensed. So that is more beneficial. For the slab calculation, you can run your slab calculation there, optimize the geometry, and then give that input to the VAST. It will give you the more accurate result.
So let me have a few questions from this side, but before it, I'll give to Dr. Subhash Pingle, who is one of the organizers for hands-on session.
I want to just add some comment or this one on that self-consistent field procedure. See, it's a one electron system we are converting, and Fock operator is there, and then that operator will operate on in wave function. Hartree-Fock theory, it's a wave function, and in DFT it's a density. Okay, it will give us energy eigenvalues and then coefficient or density. So Fock matrix is a function of either density or wave function, and then but it's not a eigenvalue equation. That's what is happening. We will not get eigenvalues, and different when Fock matrix will operate on C, then we will get eigenvalues and different wave function or different density. Then Fock matrix is a function of density or wave function. So we have to put our new wave function or density inside that Fock matrix, construct new Fock matrix, operate it on the earlier wave function or density. It will give us new eigenvalue and new wave function or density. Again, take that density, put it in Fock matrix. Like this cycle will go on, and at one these eigenvalues will get converged, means they will be very closer, and at particular threshold we will say that is converged. So this is it's a self-consisting, means Fock matrix will get constructed by one wave function or a density by itself. So that is a self-consistent. Yes, cyclic process. It's self-consistent process.
So can I have a question from this part of the auditorium? Someone has to ask the question. Someone has to bite the bullet.
So
Dr.
actually
Bahira.
I think they are experimental, or they are means
No,
you are
doesn't
from
matter.
any group or something.
They had to ask it. Dr. Bahira will ask it.
Okay.
First, can you say your name and where you from?
Myself is Bhagirat from Bundelkhand University, Jhansi. Is there any role of stress in the relaxing coordinates, and what is the optimum value which we have to choose?
How to guess your initial coordinates?
Yeah, generally when you are considering the initial coordinate and you are giving as an input to your system, then suppose you are taking first SCF cycle, then at the end of that SCF cycle you can see the stress generated on the system. So generally if you get a large value related with that particular system, then you have to say that, or you have to, in the mind you have to say that the cell which you are defining is too small for that system. So in that case you have to increase the cell size. Then you can reduce the stress on your particular system. So like this way you can correlate the stress related with your particular system. So in that case your energy value may not be a correct.
So last question from this part. Yeah, good. Made my life easier.
I'm Jisha from National Defense Academy, Pune. And I want to know, like, out of this code, which code you have to use for calculating thermodynamic properties. That means if we have to vary temperature dependence and pressure dependence, out of this code, which one we have?
Yeah, today we are going to learn the quantum espresso, right? Through that you can also do dynamic properties. Siesta is one, and the VASP also gives you that type of, means you can calculate the stress calculation through the VASP. But generally, to start with, you can use the quantum espresso or the siesta.
If I am using Win2K code, which...
Yeah, it is also
But
okay.
in that we are not having any temperature dependence calculation.
But for that purpose, then you have to again shift to the CSK or the condensed space.
As such, no code will be cooperating with that to take the input and calculate.
Yeah, generally you can get through these two codes. You can calculate.
But see, what I say is that this generation, you want to have a black box with all the capabilities. Think about this, be creative. Like you're looking at thermal properties or pressure properties. So what happens in thermal properties? Expansion. So suppose you have equilibrium distance 2.1, just put the value of 2.2. Because you know what is the thermal coefficient is there from experiment. So from that way you can mimic the thermal properties, what happens to band gap or other properties when you simply put instead of 2.1, 2.2 angstrom. Always remember, you can fool the program, okay, but you have to use your knowledge of physics, okay, because this is a black box. So just do it. So let's move on to, thanks again Dr. Deshpande for a wonderful talk. And we have little momentum which I'm happy to give her. So, you have to come on. Can you set up your computer? Aparna, can you set up your computer? So we have another exciting speaker in this session, Dr. Aparna Chakravarti, which she comes from Indore, RR CAD. She received PhD from Indian Institute of Science, Bangalore, and after doing PDF, she joined RR CAD in 1998. So I call her, she's one of us. She's as old as young as I am doing it. She's been working in a lot of different areas, including metallic alloys, the two-dimensional materials, and an oxide system. So her sort of aim, which Dr. Anurag Srivastava has done, the first talk is about theory, and the second talk by Aparna is going to be about application. So you can see, using these tools, what we can achieve. Dr. Chakravarti. Let's welcome her.
So first of all, good morning to everybody, and thanks to Professor Pandey for a very nice introduction. Yeah, thanks for the water also.
Yes.
And thanks to Anurag for inviting me to this exciting e-conference, which was the first time I experienced last year, and I was very thrilled to learn the e-concept of it. And this year also, thanks to him, I am able to attend this. And today I will be talking on one of the topics which we are doing, and it is not yet published. We have just submitted the work, and that is on Hostler alloys. So first I will do is to give some general introduction, and then sorry to say that I have changed my topic. It is still effect of substitution what I gave in my abstract book, but it is now completely different. So the basic substitutions are different, the basic materials are also different. Okay, so which one is the so effect of substitution on elastic stability? So we will discuss something about elastic property also. It's not what. So elastic property. I pressed, but maybe third. Okay. I have to press third. Okay. Yes. Okay. So elastic property, electronic property, and magnetic property of nickel and platinum-based Hostler alloys. And as you see, I am from Indus Synchrotron Utilization Division of Rajaramana Center for Advanced Technology, Indore. So I'll take just 1 minute to do some propaganda for our Indus Synchrotron in our center, where you have this at the moment only synchrotrons of the country. We have two synchrotrons, Indus 1 and Indus 2. Indus 1 is a small energy one, and Indus 2 is a high energy one. And users are welcome. So any of you or your colleagues are interested, you can come to do experiments. You have to go through the RRCAT website and find out how to apply for the beam time and all. And generally, students are given some to and fro fare and also some accommodation also. So for students, it's a good thing. So that is what I invite you and your colleagues to please explore this. Okay, now back to. This is some general introduction. So what is a Hostler alloy? Basically it was discovered by discovery, this one, no? So this is discovery of Hustler was done by Hustler on 1903, and it has a general formula X2YZ, and there are X one element, Y another element, Z another element, and X is generally for conventional. There are different type of Hustler alloys. One is different type of structures Hustler alloys take. One is this conventional Hustler alloy, where the X assumes the positions 0.2525 and 0.75, and the FCC corresponding positions of that. Y occupies 0.5, 0.5, 0.5, and the FCC equivalents, and Z occupies 0, 0, 0, and the FCC equivalents. And there are some inverse Hustler structure also, where these are mixed up. So Ni to Mng is a typical Hustler alloy which assumes the conventional Hustler alloy structure, and Mn to Niz is another one which we have worked on extensively, which assumes the inverse Hustler alloy structure. So why study Hustler alloy? Because there are some interesting properties of this, and they shows martensite, which is a tetragonal conversion, tetragonal transition from cubic to martensite, and it shows shape memory alloy property. So that means it remembers its, after it undergoes this martensite transition, it remembers its properties. Then some of the alloys show this 100% spin polarization, which has possible spintronic application. And this one has possible application for actuators, sensors, and also in artificial limbs. And then our interest is in this particular property. For the moment, which the talk I am giving now is mostly based on this property. And Ni2Mng is a prototype of this ferromagnetic shape memory alloy, or which is showing martensite transition. The drawbacks are that Ni2Mng possesses low martensite transition at temperature, which is below room temperature, and high inherent crystalline brittleness. So we want to rectify that. So there is we want to look out for some way out. So we want to probe possibilities to find better Hustler alloys with high martensite transition, and then high Curie temperature, and also low inherent crystalline brittleness. Then this is what the martensite, just a schematic, a cartoon picture. So this is what the cubic, and then it undergoes some tetragonal transition, and you can have this kind of twin microstructure. And if you have a ferromagnetic component in that, like this is NiTi, is a standard shape memory alloy which is undergoing tetragonal, which is non-magnetic. And then magnetic, it is Ni2Mng, which may have some magnetic configuration also. And then if you allow applied field, there are different properties change and all. So now outline of the talk. I will talk about problem at hand and the motivation to do that, tools used, and I am thankful to Mrinalini because she has talked about many tools. So I will be talking about just mentioning the tools I have used. Then electronic property, formation energy calculation, stability under tetragonal distortion, we will probe. Then we will probe the magnetic property. We will search for ground state magnetic configuration, total and partial moments we will be talking about. Then some mechanical properties like elastic constants and some G by V ratio and things like that. So problem at hand, this is basically we will pick up Ni to MnGa and Pg to MnGa, and at the place of Mn, which is a Y atom, we will replace Cr and Fe and see what are the property changes. Okay, so motivation is that both Mn and Cr has AFM configuration, and Cr has only one electron less than Mn. So we want to see what happens if you replace Mn by Cr. Then second is Fe, which has one electron more. On the other hand, it has and also has high atomic magnetic moment like Mn, but it has a FM configuration. So again, we want to see what happens. So what is the effect if we substitute Mn in Ni to MnGa and Pg to MnGa by Cr and Fe? What happens to the bulk mechanical property, electronic property, and magnetic property? So tools used, as she said, VASP. We did the geometry optimization, full geometry optimization, and then electronic property calculation. Elastic constants have been carried out by CASTEM and has been verified by VASP also. And the magnetic properties generally, what we will be reporting is mostly VASP data and also some SPR-KTR data, very rough. This SPR-KTR she did not talk about. Maybe sometime we can discuss about it later in outside the hall. So now electronic properties. So Ni to MnGa, what happens if you replace Mn by Cr and Fe? So this is the formation energy which we obtain from the VASP core, and this is the doping percentage. We do not call it doping because it's a very high percentage. Only when it is low we call it doping. So it is very high, so we will basically call it percentage of substitution. So percentage of substitution, and then both for austenite as well as martensite phase, we are plotting the formation energy. From here we see that the martensite phase is lower for all throughout the substitution. Martensite phase are lower formation energy, as well as if we look at the delta E. So the austenite phase, the cubic phase has been normalized, the total energies have been normalized with respect to the cubic. So the cubic austenite phase has zero energy. This is the reference energy, and then the martensite phase, which has a C by A tetragonal. I talked about tetragonal distortion. So we can see that that is something C by A not equal to 1. There is a minima here. So this is showing this is shown that for all throughout the substitution it is prone to a tetragonal distortion, and this is for substitution Fe, and we again see the austenite is higher, formation energy is higher, and martensite is formation energy is lower negative. So this is more stable for this structure also all throughout the substitution, and similarly they also show a C by A other than 1. So this also is prone to tetragonal distortion. Then what happens if we take a PT sample? So PT to MnGu if we take, we replace again Mn by Cr and Fe, and we again see the same thing, that this red one is the martensite, which is lower in energy. Here also both for Cr and Fe, and this is also a C by A not equal to 1, is having a much lower energy than the equal to 1. So this is also prone to a tetragonal distortion. Then the stability comparison between cubic and tetragonal phases in a tabular form. So here are the materials: PT to FeGa, MnGa, CrGa, and Ni to FeGa, MnGa, CrGa. And here are the cubic. This is the optimized cubic lattice constant, and these are matching with experiment quite well. I did not put the experimental values here, but they are within plus minus 1 or 2%. And wherever the material is available. Actually, PT to MnGa has been grown. Ni to FeGa and Ni to MnGa are grown, but Ni to CrGa and PT to CrGa and PT to FeGa are till now predictive materials. So for the three of them which are available in the literature, they are a good matching, and this is the C by A for the martensite phase, and there also there is good matching with the experimental results wherever the data is available. And this is the delta E. This is the difference, how much lowering of martensite phase is happening. So we see that for PT samples, this is a little bit high, and this is from the Ni sample, this energy difference is a little bit low. So that means the C by A formate this martensite tetragonal transition. We see that here, if you look at the stability, these are much more stable compared to the previous one, which we can see here. Here the energy differences between the cubic phase and the martensite phase is not that much. So now we calculate the transition martensite transition temperature as a first principle first approximation. We compute kBT equal delta E, difference between energy between two states, austenite and martensite, that is equated to kBTM, and that Tm is the temperature which we have calculated using this formula. And then we are seeing that we are predicting for some of these, we are predicting the energies, the Tms, and some of them we are actually calculating. But as we see that Ni to MnGa, we predict that it is 75 only, but it is actually 204 as I said. So what we are, at this moment, what we are stressing on is not the actual value, because it is a very crude approximation. There are other entropy and other things related which we are not taking into consideration. This is just on the basis of the internal energy alone. So this is a very crude approximation. But what we are stressing on is the trend. So what we are predicting is that when you substitute Cr or Fe, whatever, then what you are getting is a increasing trend, and that is what for certain cases where, or otherwise, for example, when we compare Na to FeG, Na to MnGa and Na to FeGa, for example. So then we can compare these values and the trend. So Na to FeGa has a higher Tm compared to Na to MnGa experimentally also. So this is where we tell that this is the prediction that it will be increasing. So that only we are stressing here on just the increasing trend of the Tm. So now coming to magnetic properties. So now we will do search for ground state magnetic configuration. So what there is in the literature, there are two things which motivated us to probe different kind of magnetic configurations, because Ni to Mg is known to be a ferromagnetic sheet memory alloy, or which is showing metal side transition. But what happens if it is Fe or Cr? So two things motivated us to probe different kind of magnetic configurations. One is that in case of Ni to Mn In, it's been a little bit off stoichiometry, but nevertheless this Ni to Mn In system, Cr, when it is replacing the Mn atom, it is shown that it is seen that it reduces the ferromagnetic interaction. On the other hand, if you dope Fe in the place of Mn, it shows an increase in the ferromagnetic interaction, which is evident from the saturation magnetization plots here. Second thing is that we see this Bethe-Slater curve. This is the J value, this exchange interaction energy, exchange interaction energy. So Cr falls much below. So Cr is atomic, bulk exchange. It shows a much more likely. It is seen that it is more likely to prefer AFM compared to Mn, and also some of the Fe shows ferromagnetic. One of the composition is showing antiferromagnetic, but this is the ferromagnetic, which is shown by the arrow, up arrow, and here it is antiferromagnetic. So Cr is more prone to AFM configuration compared to any of these Fe or Mn materials. So we probe here in this particular work non-magnetic, ferromagnetic, as well as antiferromagnetic. So antiferromagnetic, what we do? We do intersite antiferromagnetic ordering configuration also, antiferromagnetic ordering configuration, as well as intra. So by intersite, what we mean is that we have, for example, PT to MNTA. So what we do is antiferromagnetic for antiferromagnetic configuration, PT and Mn antiferromagnetically aligned to each other. At the same time, when we go to intra-sublattice, what we say is there are 4 Mn atoms in a 16 atom unit cell. So each Mn atom is antiferromagnetically coupled with each other. So there are 4 Mn atoms in this system, 16 atom unit cell. So out of that, because as I said, there are FCC equivalents also. So there are 4 atoms. What I saw it 0.25, 25, 25, 75, 75, 75, 0.5, 0.5, and 0, and the FCC equivalent. So that makes it 16 atoms. So then there are 4 Mn atoms. So 2 of them are up, 2 of them are down. Since crystallographically they are equivalent, we can replace any of the 2 Mns to be up, any of the 2 Mns to be down, and energetically we have compared that they are same in energy. But what happens we take antiferromagnetic, and what happens if we take all of them to be ferromagnetic? So what we see here, that here for Ni2 FeGa, this is FeGa, no? So for FeGa, it is higher in energy. So this is FM is lower in energy. On the other hand, from here it is, because of the scale, it is not seen, but it is also same as this because the energy difference is very low. It is very evident from here that when you take, say for example, PT system, if you take the AFM, which is the red one, which is coming out to be lower in energy. Here we are plotting energy versus volume. So we say that Mn substitute, and here also the energy difference is very low, but nevertheless the AFM is slightly lower in energy. So what we say is that Mn substituted here leads to intra-subatomic antiferromagnetic magnetic ground state. On the other hand, Fe, it is expected and it is seen that it is leading to ferromagnetic ground state magnetic configuration. So then what we do again, because the last one when we showed the energy versus C by A, we did it for FM. So now since we have seen that magnetically the Ni to CRGA and PT to CRGA are prone to rather antiferromagnetic configuration in the ground state. So we do again energy variation as a function of C by A, but this time we do in a FM and AFM both, and we see that for AFM this C by A energy as a function of C by A shows much lower energy. So lower energy means more stable. So this is also evident from, this is for Ni system, this is for PT system. So this is also very evident from here. So this energy difference between cubic and tetragonal phase are much higher compared to the respective FM, which is seen from these two plots. So this is likely to lead to an even higher TM than calculated using FM configuration, which I showed earlier in my table. So now we talk about the total and partial moment. This is a vast result, and the first one before the bracket is the total magnetic moment, and the inside the bracket are the partial moments. This is for the Mn atom and this is for the nickel atom. Nickel means wherever in Ni or Pt atom. And then what we see that the lattice parameter of Pt systems are higher than Ni systems, and that causes an increase of moment of Y atom. It becomes more localized type, and it has a decrease of induced moment on the X atoms. So there is a competition between these two moments, and which affects the total moment, and it depends on the two competing factors, and finally whatever is the final results, it depends on these two factors. So these two competing factors will decide the final total moment. So major magnetic interaction in Husserl alloys, this is just for information that there are direct exchanges and there are indirect exchanges which is leading to the RKKY type of interaction. So these are the two major magnetic interactions which are relevant to Husserl alloys. Then we did some Curie temperature calculation, which I am not going to go in detail. We do some JIJ calculation using the SPR KKR code, and we do some mean field approximation for the Curie temperature. And then we show here the Tm and Tc variation as a function of substitution, and we see that there are certain trains of Tm as a function of substitution. It increases, as we see from the energy difference between the tetragonal and the cubic phase already we have seen, and that is seen here as a plot, and this is happening for the Tc. And mechanical properties, so this I am not going to in the detail of the calculation what we are talking about. I will straight away go to the results. Before that I have to tell a little bit mechanical stability. We will be talking about now mechanical stability in terms of elastic constants. So what happens, there are two different criteria in the literature. One is Stratty's criteria. So where it says that for metallic non-directional bonding compounds, the Cauchy pressure which is given by C12 minus C44, this value is typically positive. The larger the positive value, it represents the more metallic bonding, and the negative value signifies a covalent bonding framework. Second criteria which is also important, these two are empirical criteria by the way, and this Cook's criterion says that if G by B, where G is the shear modulus and B is the bulk modulus, if their ratio is greater than 0.571, the materials behave in a brittle manner. The higher the value of G by B, the more brittle are the materials. And this is phenomenologically found to be true. So what we are showing here, first we are showing calculated values of our C by, this is for Ni2MnGa, sorry this got garbled up, I don't know why. This is Ni2MnGa, these are the values, these are our values for C11, C44 and C12 and B etc. And then this is from some reference which is calculated values, Zayak et al. And these are the two experimental values, and this is for Mn2 and IgA, this is our data, and this is also an experimental data which is listed here, and we see there are very good matching, in most of the cases it's quite good matching with the experimental data. So we get confidence that our calculations are correct. So then we do listing of elastic constants of our materials, Ni2MnGa, cubic phase, tetragonal phase, Pd2MnGa and tetragonal phase. I am just picking up these four just to show you just one point. One is that what are the G by B ratios, that is what we will be talking about, we are seeing here. That Ni2MnGa in the cubic phase it is 0.42, whereas PT sample has a much lower G by B ratio. So you can understand from the previous slide what I talked about. So this will be more brittle than the PT sample. So the effect of substitution of PT on Ni leads to a very lowering of the brittleness. First thing, that was one of our searching, one of the things which we were searching for. One was high Tm, one was high Tc and low brittleness. So this shows low brittleness. And what we are more important is that if you look at the cubic phase, the C prime is softened. Whereas if you have the, and this is the C prime is the tetragonal shear constant. If you remember your MSc from Kittel. So then this is what is much lower, and here it is even negative. So there is a lot of softening of the C prime values in the cubic phase. On the other hand, tetragonal phase there are very high positive values. So this indicates that these two materials are very prone to tetragonal distortion because their C prime in the austenite phase is a very much softened. And this is 2 minutes, almost done. So this is what is a correlation from literature, and this shows a linear relation between the Cauchy pressure versus the G by B, and this ductile and metallic bonding, and this is covalent and brittle bonding, covalent bonding and brittleness. And then from our calculations we see that these are the materials, and these are the overall roughly correlation constant is not that great, but nevertheless it has a tendency of linear trend. And here is some of our older results which is not really visible, sorry. So there also we see some amount of quite a nice linear trend. So we say that the linear trend is quite general across the materials. So that was given by somebody else on some different materials, as you can see here. So various different kinds of material, and what we are doing here for these two curves are only for Hustler alloys, this one and this one. And we see that, so we say from here that the linear trend is quite general and it is varied across materials. And some of the other results are also showing that, that's what we are showing here. Then summary, Ni2Mng and Pt2Mng substitution, we see the substitution of Mn by Cr and Fe leads to stable compounds electronically. And then when we see compare the Ni based system, Pt based systems are showing predicted to be showing much larger energy difference between the cubic and tetragonal phase. So they are expected to be showing more stable tetragonal phases compared to Ni based systems. Both Ni and Pt based systems show almost volume conserving structural transition cubic to tetragonal, which I didn't show here, and that indicates that there will be one of the indication is that will be showing a Martensite transition. Then Mn substitution by Fe leads to ferromantic downstate, but Mn substitution by Cr leads to intra-sublattice antiferromantic downstate. In acknowledgement, all the collaborators, all my collaborators, specifically T. Roy, S.R. Burman, he is my experimental collaborator and he is my student. Then Sanjay Singh, Sunil and C. Kamal, they are students of mine and this collaborator. And all the members of ISUD and my division head, director, and HBNI, Homigawa National Institute. And finally, thank you very much for your attention.
Comments, suggestions? I think since you've been asking, a lot of questions, let me ask someone else to take you become the last. So we have only 3 questions. Yes. Please use mic.
I am Gaurav, I am working as a student professor in Punjab University, Chandigarh. And my question is, you have discussed about the replacement of Ni by Pt and talk about the brittleness of that material. But have you touched upon the doping concentration?
Which concentration?
The doping concentration of Ni and Pt, that will also affect the brittle behavior of that?
Yes, yes, we have, that is our previous work which I showed here in this one. This is actually already published in JALCOM. Here we have shown 2 substitutions. One was Pt substitution at Ni site and copper substitution at Mn site. And both of them are very favorable. So if you go from that, in that JALCOM paper, the final conclusion is that if you go from Ni to MnGa towards Pt to CuGa, so you have to have because Pt to CuGa is completely non-magnetic, but we are looking for ferromagnetic Scheck-Miller. So, but in between somewhere you should be getting a ideal composition where you have both ferromagnetism as well as less brittleness as well as high Tm and things like that. But mind you, this brittleness is inherent crystalline brittleness, which I should mention, because actual brittleness of the material will depend on many other things like defects, dislocations, etc. But here we are talking about only inherent crystalline brittleness. So this is just a, I would say, foundation. On top of that, when you actually make the material, then you may have many kinds of defects and all. So that will actually add to your problem. Either it will help you or mostly it will help you, but it may not help you also. The brittleness may be different. But from the first principle calculation on pure samples, this is the prediction.
So in your experiment you have come across?
No, I didn't do experiment, but some of these things are already this Sanjay Singh and S.R. Burman, we are doing in collaboration with them some experiments also. Means I am not doing experiment, they are doing the experiments.
Question from the side, middle.
But she has also asked previous. She wants, but she also.
They will not be given the chance.
Given chance.
From this bench.
Last chance.
Just ask anything. Don't worry about it. Whole idea is to encourage you to ask questions.
Yes.
You have decided the property of antiferromagnetic.
No, he is already talking to them, no? Cross-talking.
No cross talking.
No cross-talking.
Okay,
He has
yeah,
a
he can
question.
ask a question.
He has done some work on this alliance.
Acha, Western Alliance. Oh, good. Follow.
You have decided the property antiferromagnet of a ferromagnet using the total energy conservation. So we can also satisfy this criteria using the polarization value.
Polarization.
Yeah.
Polarization we are not calculating, but what energetically which of the configuration is stable, that is what we are looking at here. But polarization, I don't know exactly how to do it.
Some of the papers write the polarization is greater than to 0 or less than to 1. That is ferromagnet. So this criteria for this or not?
I don't know this. I am offhand, I don't remember.
You can talk with Madam Lake.
Okay.
Yeah. So let me give you a chance to our bright students.
No, there is one more question.
My name is Pawan Sai from Amity University. My question is, how do we calculate G by B ratio?
G by B ratio, you calculate the G and the B, that we can discuss later, I can tell you. So you calculate the shear modulus, you calculate the bulk modulus from the C values. It is there in the, it is elastic constants, right. And then from there you can calculate the G by B ratio.
What would be the variation under minute pressure?
Pressure actually we are doing now, because pressure is a non-equilibrium, non-ground state calculation, no. So you have to be always very careful about that, because what we are doing is a equilibrium ground state calculation. There we are predicting, but as soon as you go to pressure or temperature, this becomes a non-ground state calculation. So you have to be very, very careful, and maybe sometimes you have to take help from the experiments and then try to see whether your predictions are going correct in a correct way or not. We are trying to do some pressure variation also.
Let's have the last question.
Okay, hello everyone, I'm Saurabh from IIT Indore. Ma'am, I have one question, like how to calculate MAE in WASP?
What?
MAE.
MAE.
Magnetic anisotropy.
Oh, magnetic anisotropy. This I have not done yet. So maybe I will discuss with you later, because I have not done yet anisotropy calculation. So I am not really able to tell you right now.
You want to comment on how to calculate MAS WASP?
That's all.
Means we have to do the non-collinear calculation, and you can calculate.
You can talk about it.
Okay, we can discuss about it, because I also wanted to start, but till now I didn't do it.
There are in VAS there are some flags. You can set those flags, and non-collinear
Non-collinear
calculations
is
you
there.
can do. Non-collinear calculations you can do in VAS.
On WASP page they mentioned that we have to perform some like collinear calculation.
Collinear
Yeah. First you have to run the collinear calculation. First you have to run the collinear calculation. Then you have to use the non-collinear flag. Set that flag and run the calculation for different directions.
Yeah.
Because I am confused about like those tagging.
But you can
Let's
discuss it.
We will have discuss
sure.
in a detail.
But let me just take 30 seconds. Can you show your TM slide?
Yes.
And see how beautiful example is Dr. Chakravarti has taken the energy difference and sort of converted to what you question about the thermal property.
Yeah.
So it's a very, very rough
So,
approximation.
the
You have the
table,
table.
Huh.
Here.
No, yeah.
Yeah, here.
Look at this energy difference, simply she has taken as kBTM.
Yeah.
Is the temperature induced phase transition. So although it's a very, very rough approximation, but you can see beautifully it sort of follows the qualitative understanding of the system.
Exactly.
And always we should shoot for qualitative rather than quantitative. Because this is again involves a lot of approximations. And this is one of the examples which I really like very much. Just shooting a simple insight and getting the sort of physics or chemistry of the system right. So thanks again Dr. Chakravarti for this talk. I have a little memento to give you.
Oh, yes.
And we have a photographer ready?
Yes.
Hello. So let's take out this.
Hello. Yeah. Yes, I can hear you.
Oh, he's already online.
Yeah.
So he's coming online. He's online. Is he? We're going to see his face.
45 minutes. These are 15 minutes, 45 minutes. Half an hour. इकट्ठा वो ऑल इन्फॉर्मेशन मिल जाता है, नहीं तो हमको
So since they are setting up this thing, do you want to again have a dialogue about the collinear versus non-collinear calculations? So what was the thing you said is you did collinear calculation and then you tried to do non-collinear.
No, he wanted to know the anisotropy energy.
Agreed. So what is the problem with the non-collinear? Tagging.
Tagging
means what?
Tagging is like how to give instant
So in the in-car file, when you are using non-collinear, you have to use the non-collinear flag too, and then on each atom you have to give the direction.
Magnetic
moment you have to specify
X, Y, Z.
X, Y, Z.
But when I'm giving random basically, then that basically I have to choose from previous collinear calculation.
Yes. This is again it becomes easier. But what I tell the students is take the non-collinear tags, but mimic the collinear first. So you know what you're doing is correct. The number should be the same.
And we have to use previous charge card or flip card.
No, generally we don't, means if you are shifting to a non-collinear, then generally we are not preferring the previous char density. We have to take one self-consistent run with the non-collinearity and then go for the optimization. It will enhance the speed.
I don't do many calculations because they are really paid in math.
No. But
ना कोलिनियर का चार्ज का लेना पड़ता है.
नहीं लेना पड़ता है. But if you
कोलिनियर
use
का चार्ज का you can take.
But if you use means the flag value, which is means I start value, if you are taking as 11, then you can take the char density from the collinear one. Otherwise, if you are from the collinear one, if you start with the fresh one, then you have to build the char density with the non-collinear.
Play around. Any other comments, questions? Middle section?
Non-collinear.
Yes. Please.
मैंने anisotropy energy नहीं किया. Non-collinear.
Dr. Chakravarti, there is a question.
Ma'am, actually I want to know what is Cauchy pressure.
Cauchy pressure. Cauchy pressure is that expression is given. So it is based on the elastic constant.
What actually it means?
What does it mean physically?
Physically, therefore C12 minus C44, so it is a difference between two elastic constants. So physically, I don't know, means it somewhat as the criterion says that it gives some kind of indication of the bond. So that much I can say. Beyond that,
what it means Cauchy discrepancy also it will be telling in some other papers and I've seen later Cauchy's discrepancy.
Discrepancy between what?
Cauchy's discrepancy is another term they are using.
Another term for stability.
Cauchy discrepancy.
Yeah.
I don't know, maybe if you can show
See,
your Cauchy pressure.
If I can,
Yeah.
so what are you looking for? Mechanical property.
Yeah.
Why are you calculating elastic constant? What is the reason?
How much?
Structural stability. So all these criteria they devise is again a quality empirical criteria to see how stable or how brittle, what Dr. Chakravarti said, is how brittle the system is. So she doesn't care about the magnitude. She cares about is with platinum and a nickel, there is definitely a big difference. The platinum case is less brittle than the nickel case. That's only we can say. You can ask the degree of brittleness.
Then what will the answer?
Qualitative.
Qualitative.
Do not go for quantitative matching. And always remember, every experiment has error bar. You calculate the bulk modulus. Can anyone say what is the error bar in experimentally measured bulk modulus? Yeah, no. What is the error bar? When the experiment is called bulk modulus value, what is the error bar? Can you guess?
तब तो connection हो गया था.
You know, experimentally say my bulk modulus is 200 gigapascal. So what is the typical error bar in this value, 200 gigapascal? Up to 20%. Up to 20%. So always remember, but you have 200 GPa bulk modulus, which is very easy to measure. It's a very, very high error bar. It can go from 180 to 220.
See, experimentally, I do not understand why that error bar. Theoretically, it's a second order effect, so it can lead to differences. But experimentally, why
the error bar is because of the high pressure measurements.
Oh,
okay. And you don't know exactly 4 or 5 GPa.
Okay.
Same with the energies. You know, all these things, they always have an error bar.
Yes, sir,
So next speaker, Dr. Ghosh from Pune is here. Can you hear us? Dr. Ghosh? Is he on?
Okay.
Can you hear us?
Yeah, I'm able to hear.
Good. So the last speaker of the session is Dr. Prasanjit Ghosh from Pune, and he's received his PhD from Jenkar, Bangalore. And after doing postdoc at ICTT Trieste, he's joined ISER Pune, and he'll give us sort of a brief introduction about the topic is what is quantum espresso and what it can do. And where is he? Dr. Ghosh, we have about 30 minutes.
Okay.
I'm keeping about 15-20 minutes for a lot of questions. The
okay.
Students are very eager to ask a lot of questions.
Okay,
Go ahead. Let's welcome Dr. Ghosh.
Shall I start? Good morning, everyone. So shall I start?
Yes, please.
Good morning, everyone. So I first of all would like to thank Professor Anurag Srivastava to giving me an opportunity to return what I have learned from the community to back to the community. So what I am going to do is over the next 30-35 minutes, I will briefly tell you about quantum espresso distribution itself, which Eminem was supposed to tell you in the last evening, and then the practical aspects of doing a reagent calculation using quantum espresso. So what I will do is I will try to correlate the theory with the different flags used in the input files. And then post this session, my students will conduct a hands-on session. First, they will do a calculation of silicon bulk, and then nickel to show how to treat bulk nickel, to how to treat magnetic metals, and then the calculation on hexagonal boron nitride, a sheet of hexagonal boron nitride to show how one treats finite or nanosystems. Okay, so the quantum espresso, the full form stands for Quantum Open Source Package for Research in Electronic Structure and Simulation and Optimization. And if you go to the website, you will find details there. So I'm not going through those. And then, so they have also a wiki here where you can find a lot of information, both technical as well as the fundamental information. And then there is a developers portal, www.kiwicodes.org, from where you can download. And there are two mailing lists, one for the developers to do new announcements, and then there is a very active forum where there are a lot of interesting general discussions can be posted by the users. And so there are two main packages of quantum espresso. One is called the PW, which is basically used to perform self-consistent electronic structure calculations, then relaxations, and also you can do Born-Oppenheimer molecular dynamics. And then there is another package called CP, which does not Oppenheimer molecular dynamics. So these are the two basic structures, and these are connected to several other packages. For example, go on to do linear response calculations, then there are post-processing packages, then there are packages to generate pseudo-potential, and then there is also a graphical user interface to generate the input files. Apart from that, there are also standalone packages which are or which can read in the inputs from the output of quantum espresso. So for example, if you are interested in looking into linear functions, you can use linear 90. Then for ballistic conductance, there is PW-CON. Then you can calculate fixed near-edge X-ray absorption spectra. Then you can do calculate EPR and NMR shifts, and also GW calculations, PDD calculations. So the list is not exhaustive. I've just put in a couple of them. And so what you can do with quantum espresso, you can do variable types of calculations. You starting from non-conserving, ultrasoft, core, and there are again a variety of flavors of exchange correlation functionals which you can do. So you can also handle spin polarized calculations as well as non-collinear calculations, which are the spin orbit interactions. And again, it's a long list, so these are just to mention a few points. Okay, so coming back to today's agenda, so what the next half an hour or so, what I will do is, we will talk, we'll learn how to do a total energy calculation, which is the first step in any calculations you do using density functional theory. So I hope there has been an introduction to density functional theory from the earlier speakers, so I am not going into details. So what I have here is the Constant equation which we are interested in solving. So the first term is the single particle non-interacting kinetic energy, then you have the nuclear, electron nucleus potential. So this comes in as an external term because we solve the Constant equations for a fixed position of the nucleus. And then you have the Hartree term, and then whatever is left, for example, the exchange and correlation, and then the interacting kinetic energy part, the difference between the non-interacting and the actual interacting kinetic energy part, all these unknown quantities, they go into the exchange correlation potential, this V x theta. And if you look into this equation, so our unknowns are the wave function, and our Hamiltonian depends on the unknown through the density. Hence, we can't directly solve this equation, and it needs to be solved self-consistently. The self-consistent loop is shown below. So we start with a construction or with a known form of the nuclear potential, that is the electron-nucleus interaction. Once we know that, we start with the initial guess of the density. Then from there, we calculate the Hartree term and the exchange correlation term. Once we know all the three potentials, we can construct the effective potential. And then we diagonalize Hamiltonian. From there, we generate the new density. So we check whether the new density is significantly different or they are similar to the old one. And if there is no change, then we come out of this loop, and then we calculate different quantities like energy, forces, etc. And if it's not converged, so we fit the new density goes in as a fit as an initial guess. And then we repeat the loop till the calculations converge. So this is the framework of the self-consistent iterative solution. And in order to do this, what we do is we expand the wave functions in a basis set. So, for example, here the wave function psi I have written as a linear combination of some functions f alpha r. And once you plug in this equation, then your eigenvalue equation is given by this, where each alpha beta are the matrix elements and hi are the eigenvalues and c I alpha are the eigenvectors. So C's are the coefficients of the which comes into the expansion of the wave functions. So once we diagonalize the matrix and calculate the eigenvalues and eigenvectors, we get our energy spectrum along with the wave functions. And the size of this matrix depends on the size of the basis set in B. So at the end of the day, you need to diagonalize a NB cross NB matrix. So there are different types of basis sets one can use. So the simplest and the most commonly used basis set in the solid state physics community are plane waves. Then you can also use a localized basis set. Also you can use a mixture of two. So different codes use different types of basis sets. For example, yesterday there was a talk with Siesta where they used a mixed basis set. However, quantum espresso uses the plane wave. Accurate and convenient and Calculation for this type of system, what you need to do is you So as you see that my main things have been depicted here. For my choice itself, you need to use a large matrix in the real space to simulate a surface or crystal or a nanotube or a plasma. So as I mentioned earlier, so since we are using a large matrix cell in the real space, so the reciprocal space, the G vectors, they tend to come much closer to each other. Okay, so when you try to find the basis thing, so you will have large G vectors in your name expansion, and this increases enormously your computational cost. So similarly, you can also simulate, for example, defects like latency or impurities, or you can simulate lossy crystalline amorphous systems, but these are very expensive simulations. This time, so for the artificially created systems, what we need to do is make a large unit cell. So you have a long M1, A2, A3 lattice vectors, as I mentioned before, and that implies reciprocal space to have short M1, B2, B3 vectors. As a result, many G vectors will fall within the same pattern as you are controlling. That increases information. So once you have determined, once you have defined the system to the code, so how is the vector potential evaluated? So right now we are in this first part of the self-consistent. So you all know that in crystals, in any solid systems, the electrons exhibit or display circular potential. So this has a simple form, but has not yet been very in this divergence. This leads to computational problems. But if we look into the chemistry of the type of interactions which electrons between two atoms, electrons which take part are the valence electrons or the mode electrons. So what is typically done is one raises the mode electrons. And so here what I have is for aluminium with 7 obviously having this nodes coming into this calculations, and you need a larger basis set to represent the wave function. Or in other words, it becomes expensive. So one needs to have a certain balance between the accuracy and the computational costs on which have base set to make this kind of calculation. So the ultrasound superpotential proposed by David Adler, what he did is he relaxed the conserving conditions, and as a result, I'm not going into details because that will itself require one full lecture. You can push the RC to higher values, and you can have software potentials, and there are tricks by which you can get similar level of accuracy. So the variety of types of potential we use is primarily depends on the type of elements you are trying to have, and for each type of potential you need to depend the convergence basis of the interface basis. So this varies from the different potentials. So for high complex potentials you will have smaller value, for other potentials, for example non-convergent potentials, you will have a much larger value. So the fundamental question you have a library of potentials. Go to the website, there is a theory table where you can determine what type of functional you are interested, what type of pseudo potentials. And so for most of the elements, there are different pseudo potentials available. Also in the UV code website, there is a pseudo potential library which you can download and install and use those. But one piece of advice here is whichever pseudo potential you use, whichever source, do not use them lightly. One should test the pseudo potential system, see that they can reproduce the properties of the simple system, and then go to use the pseudo potentials to do calculations for other for your present manual system. Otherwise, there might be some problem with the pseudo potential, and you might end up with wrong results. So testing of the pseudo potentials is a must when you do any calculations. So the base potential files are mainly quantum espresso. So for example, here I have just taken a screenshot of one of the potential files for oxygen. So the first it defines the type of state correlation function, in this case it's PPE. Then it defines the method in which the exchange correlation function are generated, and also along with it whether it's a non-conserving or backward or ultrasound. For example, RRTJ stands for the PPE exchange correlation that functional and the pseudo potential generated with this Rayleigh method, and US stands for these are ultrasound type of functions. So the pseudo potentials are mentioned in the input file under the atomic underscore species card. For example, for barium titanium, BATI for calculation, BATI 3. First we mention the species type, barium, then the atom mass number, and then the name of the pseudo potential type which you are trying to use. So similarly for titanium and for oxygen. And as I mentioned before, so E-contact function determines the size of the plane basis set. So when you are using ultrasound, you need another grid which is for calculation of the charge density, and which is determined by the size of the E-contact. So typically, for potential experience, let's say that the size of the E-contact is 1 or 2 times the size of the E-contact function. And another thing is when you are having to mix different types of elements, so you should be sure that the pseudo potential which you are using, they are using the same exchange correlation function. For example, suppose you are doing one simulation calculation for iron cobalt alloy, you cannot use local density type of exchange correlation function for iron and the cobalt type of exchange or a PGA, PV type of exchange correlation function. The reason, and if you do that, the code is not enough to understand and complain about it. The reason for this is when you have the material, you can't distinguish that this electron belongs to iron or this electron belongs to cobalt. So for that reason, you need to treat all the electrons in the same coding substance. So this is something one should be aware of. Okay, now coming to the step 2. So once we have constructed the FPL or the Plutonian. So then we need an initial guess So once you have the initial guess, now next step is to determine the exchange correlation function or the potential corresponding to the exchange correlation function. So as I mentioned before, all the many-body information that goes into the exchange correlation potential. So the exchange correlation potential is known from quantum particle calculations or numerous other numerical calculations, quite reasonably accurate from homogeneous electron gas. So starting from there, one can make approximations from the exchange correlation functions or present system. So what if there are most popular approximations are the local density approximations and the generalized gradient approximations. So in the local density approximation, what is typically done is, for example, if this weak cube is the simulation of where the electrons are, so what does is one divides this weak cube into several small cubes, and in each of these cubes, the density which you have, you replace the exchange correlation function for the homogeneous electron gas with the having the same density as the density of electrons present in this cube. Okay. And then you do the integral, and then you integrate to the volume to get the exchange correlation energy. So if you see, I mean, this is a very good approximation in the sense it doesn't take into account the variation of densities as you move from one small box to another small box. So typically for alkaline metal types, this approximation works very well. Also, it works surprisingly well other systems where electron density is not so homogeneous. But a more accurate approximation is another level of accuracy is when you take into account the gradient of the density also. So your exchange correlation function, the potential VXC in the LDA is just a function of density, but if you incorporate the gradient of the density, how the density changes as you move from one box to another box, then there are these gradient approximations, the general distribution approximations. So for example, PW91 and TBE. So these are two different levels of gradient approximations. So apart from this, there are also a lot of there is a wide family of exchange correlation functions, and for example, even hybrid exchange correlation functions, you have beta GGS, and so on and so forth. Again, this with a separate topic discussion and also a topic of research. So once you have decided the exchange correlation functional and you have found out the effective potential, so what you do is you go and diagnose your field unit. And this is the most expensive part of this whole SCM. So in order to diagnose the field unit, so you basically do a matrix diagonalization. The size is determined by the number of plane waves that goes into your basis set expansion. However, you don't need all the so you don't need to diagnose the full matrix. Typically, what we are interested is only the open states and maybe a few empty states. So one can try to obtain only the lowest few eigenvalues. And nowadays there are some proteins which can give the diagonalization and give you only the lowest few eigenvalues which you are interested. And also, since the exact diagonalization is very expensive computationally, so most of the codes don't go into exact diagonalization. The other one uses the iterative diagonalization. And that because, so basically what is done here is the diagonalization is requested to minimization problem. And the input parameter for, okay, so there are different options of diagonalizations available in quantum espresso. For example, we use BFGS, use Nodule gradient, so on and so forth. So what type of diagonalization routine you will use is determined by this parameter diagonalization. So the default is BFGS, which is typically pretty fast. And how many eigenvalues you need for the diagonalization routine to return, that is determined by the parameter in time. So basically that's the number of states for which you want to return the eigenvalues, and it depends on the number of electrons. For insulators, it's in mind is not the number of electrons in the system for electrons, slightly more. And also, okay, so this is thing you come in later when you talk about sample. So once you have got
So I think since chai is getting cold, we can tell Dr. Ghosh his internet is not working. Can we? Yeah.
Okay, so actually when the calculations are done, they are done in the irreducible part of the Brevin zone, highlighted by this red, this yellow triangle here, and you can take the weighted factor of each of the k points. So the k points are given by this flag called k underscore points in the quantum espresso. So you can there are different flavors of k points, and you can mention it in different ways. So you can generate an automatic grid using the automatic term. You can mention them in terms of the crystal coordinates. You can do a gamma point calculation. To use automatic, then you need these 6 additional flags, which determines the dimensions among each of the 3 vectors in the reciprocal space, and then you can use a shifted and an unshifted element. But for the metals, one need to be careful. It's a bit more complicated because, for example, for metals, the Fermi surface cuts the bands, and the occupation number. If you look into the Fermi-Dirac distribution, so it's a discontinuous function at the Fermi energy. So typically, because of the discontinuity in occupation, one uses some smoothing functions when handling metals. And the input parameters are for occupations, you can say use a fixed, or when you are doing with insulators, and then for metals you can use smearing, and then there are different types, smearing or smoothing functions, and you need to choose a broadening parameter. So when you do the calculations, you need to check convergence test for each of the k-point mesh and the value of the decos which you use. So once you have done the convergence, so once you have generated the density, then what to do is you check the convergence. So you check with how the density is different from the previous iteration, and that is controlled by the input parameter convergence underscore threshold. So typical values for this is 10 to the power minus 6 to 10 to the power minus 8 of that order, depending on what level of accuracy you want. So once you have, if your convergence criteria is satisfied, then the code comes out and does other sorts of calculations, and if not, then this input, this new density goes in as an initial guess for the next iteration. But if you directly just feed in the initial guess and the new density as the initial guess, then it may not converge, and often it doesn't converge. So what people do is typically they use mixing. So what one does is one typically takes some combination of the input from some combination of the input and the output densities, and then they add them up and give as the input for the new iterations. So you can take, say for example, for the older densities, you can take from several previous iterations and do the mixing. Okay, so the idea is to achieve the self-consistency as quickly as possible, and this is determined by the mixing mode. So there are different ways of mixing the charge density in the quantum espresso, and then determine how much is the mixing done. That is determined by the mixing meter parameter. So once you have done the mixing, so what you do is you go to you fit them in your SCF loop and you go on without that. So once on the other hand, if you come out or if you have achieved self-consistency, what you can do is you can calculate the forces, and then according to the forces you can move the ions and go on for example for a geometry relaxation. So you can do many things with that, and I think so with that I end here. So this is the main SCF, many of this with the different parameters, and you'll see more of it in the hands-on session later the day today. And so one thing I'd like to acknowledge about the slides is the slides are be taken from previous books by Shobna, lectures by Shobna Narasimha Pichini, and some lectures from Nicola Madhuri's open course software. So these are all available in the Quantum Express website. And thank you.
So let's test to Dr. Ghosh. Quick questions. We have one or two. The chai and coffee is getting cold, so I'm not going to push it. But we have Niharika. Where is Niharika? Can you stand up? Niharika and Subramaniam are here. They are working with Dr. Ghosh, and I think you'll be conducting the hands-on session. So please ask a lot of questions to them. Thank you. Thank you, Dr. Ghosh. And let's thank again all the speakers, including Dr. Deshpande, Dr. Chakravarti, and Dr. Ghosh.
तो हम दूसरा जगह जाएंगे ना